Good morning. The harmonic oscillator is one of the simplest quantum systems, and it's one of my favorites. It has applications in quantum computing, particle theory, electricity and magnetism, quantum optics, solid-state physics. It's everywhere. And it's the subject of 3 of my videos. There's an upcoming video on quantum optics, which is the topic of the 2022 Nobel Prize in Physics. A few days ago, I published a video presenting the power series solution to this problem. That was necessary to lay a foundation for an upcoming video on the hydrogen atom. And today's video shows an easier, more enjoyable method of solving the harmonic oscillator, the Dirac method of raising and lowering operators. There will be a link to the companion video in the description below. So this is the quantum mechanical version of a mass attached to a spring, oscillating back and forth in one dimension. It exhibits energy quantization, and it provides motivation for the concept of the photon. The main importance of the companion video is that it introduces the method for solving the hydrogen atom. The purpose of today's video, is to show how algebraic methods can save us from the pain of solving differential equations by brute force. The equations I'm presenting follow the notation from and the overall strategy of Griffith's undergraduate textbook, Quantum Mechanics, and you can probably find a PDF, a downloadable PDF version of this book on the internet. So let's dive into the mathematics. We're going to use certain basic concepts from calculus, differentiation and integration, complex numbers. So figure 1 introduces the derivative, and what we have here is it's a limiting process. We have approximations to the derivative is like the slope of the curve at the point where the arrow is. And we approximate it first with the sky blue line, then the purple one, then the red one. Each time we get closer to the answer, but we don't reach the answer. It's like a limiting process, and it's the slope. Now this curve is a parabola. It's governed by the equation y equals x squared, and the derivative is 2x. So for instance, where the arrow is, x is equal to 0.8, and if you look at it closely, the slope of these lines, as you get closer and closer in, comes closer and closer to 2x, to 1.6. So that's the derivative. The second concept we're going to use is integration. Integration is the inverse of taking the derivative, and the derivative is the inverse of taking the integration. They go in opposite directions. So I showed you on the last figure x squared, and I took its derivative and we got 2x. Now going in the other direction, if we have 2x and we integrate it right here, we get x squared. And what it is it's the area under the curve. So this diagonal line here is the curve. Well, it's a straight line, but I'm calling it a curve. given by y equals 2x. And if you look at the area under it, summing up the width times the height of all these rectangles, as you can see, the increase in area as you move to left to right, the area increases more and more rapidly because the rectangles are getting taller. So that says that the integral is not a straight line, it's a parabola. It's the curve x squared. The next concept we're going to need is imaginary numbers. Complex numbers, really, but the one we're going to see is the number I. It's the square root of -1. And the way this works is complex numbers live in a plane, a two-dimensional plane, like on a piece of graph paper. And the horizontal axis, right here, is the real part, and the vertical axis, right here, is the imaginary part. And if you have a complex number, like here I've given 3 plus 4i, the real part, if you drop down vertically, you come down to 3. So the real part is 3. And if you go horizontally, you come to 4i, and that's the imaginary part. Really, 4 is the imaginary part, but I mean, the language is ambiguous. If I say the imaginary part, I might mean 4 times I, this point right here, or I might mean that it's 4 on the imaginary axis, so I might say the imaginary part is 4. The final concept we're going to need is operators and commutators. An operator takes a function. For today's presentation, a function is like a curve on a graph, and it takes that as its input, and it returns you another function as its output. So these operators, like taking the derivative or taking the integral, those are operators. And some of these operators, it matters which order you do them in. So if I do A first and then B, I get a different answer than if I do B first and then A. And that difference is called the commutator. And it's very fundamental in quantum mechanics, not just in today's problem, but in general, and we're going to use it. So let's dive into the derivation. When you're dealing with quantum mechanics, ordinary quantum mechanics, non-relativistic quantum mechanics, the kind that was invented in the 1930s, you have an operator called the Hamiltonian that's always indicated by H, and a lot of times they won't even tell you it's the Hamiltonian. You're just supposed to know that if it's H, it's the Hamiltonian. This funny hat over the H, the inverted V, it's called a hat, and I use that to distinguish numbers such as the mass from M from operators. The hat, if there's a hat, it's an operator. So this is the Hamiltonian operator, and what they say about it is that it gives you the total energy. Sometimes it's a matrix, but right here it's not. It's a combination of functions and derivatives. P is the momentum operator, and M is the mass. It's a scalar. It just multiplies or divides. So if it's an operator, it's a very simple one because it just multiplies. Omega is the natural frequency. That's the frequency at which the masses would oscillate if this were a large system that wasn't quantum mechanical. X is the distance from the 0 point, from the point where the mass would come to rest if it were possible for it to slow down and stop. It's the center. So this is the Hamiltonian. Here's the momentum operator, and Schrodinger just sort of pulled this out of his tail, pulled it out of thin air. It's a derivative. H bar is Planck's constant. It's a very small number. It's like 10 to the minus 34. And it's a measure of how small you have to get before quantum mechanical effects become important. I mean, there are a few large systems that are quantum mechanical, like superconductors and superfluids and maybe a few others, but usually it's something tiny, and that's because h bar is a very small number. I is the square root of minus 1. D by dx, that's the derivative. So to get the momentum, you take the derivative of the wave function. I'm going to show you the wave function in a moment. And then you multiply by h bar over I. That's the momentum. Now, this expression for the Hamiltonian, you can find this in a textbook on classical physics, except for there won't be a hat over p because p won't be an operator. It'll just be the mass times the velocity. But it's the same formula. Only in quantum mechanics, p is an operator. Here's the potential energy. The slope of this curve is what's called the restoring force. It's the force that would tend to push the particle back towards the center. And as you can see, the slope increases as you move away from the center. And that reflects the fact that as you move away from the center, there's a greater and greater force trying to push the particle back to the middle. So that's the potential energy. It's part of the Hamiltonian because it contributes to the energy. Here's Schrodinger's equation in its most abstract form. This is what's called the time-independent Schrodinger's equation. And what that means is it's the one we use to get energy levels. So if we substitute equation 2, the formula for the momentum operator, and we substitute that into the Hamiltonian H, and put that in equation 3, then this is what we get. And this is Schrodinger's equation. So psi is the wave function. That's what we're trying to get. We're trying to find the wave function, the shape of it. And if it's complex, we'd be looking for the phase as well. H bar, Planck's constant, m, the mass of the particle, omega, the natural frequency, x, the distance from the center, psi, the wave function, and E, the energy. In this type of problem, the energy is constant, but we need to be clear about that. There's more than one solution to this equation. There are different solutions, and for different solutions, the value of E may be different, and in fact, for the harmonic oscillator, it is. So E has multiple values, but there are gaps between energy levels. You might have one energy level here and one here, and the particle can't be at an energy in between. That's quantized. That's quantum. And it's characteristic of any quantum particle that's confined to a small region. The energy gets quantized. And one of the main results of today's derivation is to determine the possible values of the energy. And what this does in a realistic system is it determines the nature of the photons that are absorbed and emitted as the particle moves from one energy state to another. So it determines the color or wavelength of the light. And for the hydrogen atom, that was a big challenge for the physicists of the 1930s to explain the characteristics of the photons that were emitted and absorbed by hydrogen. This is called an eigenvalue equation. This one right here, the one I've highlighted. This is a term from linear algebra. E is referred to as the energy eigenvalue, and psi is occasionally referred to as the eigenfunction. Eigen, I believe it has it's a German root, and it means characteristic. So this is a characteristic equation. Now, equation 4 here, it's a second order, linear, ordinary differential equation. Second order because right here we have d by dx squared. We take the derivative and then we get a result, and we take the derivative a second time. So that makes it a second order differential equation. It's linear because psi doesn't get squared. It just gets multiplied. Number gets multiplied by psi, or the derivative gets taken. So if you had two wave functions, two solutions, you could add them together and the sum would be another solution. That's what's meant by a linear equation. So factoring out 2m from the equation for the Hamiltonian, we get equation 5. It's very similar to what we had before. We've just kind of combined the factors. We put this in parentheses. And Schrodinger's equation then looks like this, equation 6. And notice one thing here. We've got p squared, the momentum squared, and we've got mwx squared. So we've got the sum of two squares. This might remind you of an identity from high school algebra, where we express the difference of two squares as a product of two factors. A squared minus b squared, if you work it out, it's equal to a minus b times a plus b. Now, we can't quite use this in the form it appears here because we don't have a difference of two squares. We have a sum of two squares. We have p squared plus mwx squared. Now, to get the negative sign, we have to introduce I, the square root of minus 1, because if you square I, you get minus 1, and that gives you that changes this minus sign to a plus sign, you see. So these are the two factors that multiplied together give you the Hamiltonian. They give you the left-hand side of equation 6. A is called the lowering operator. A dagger is called the raising operator. And the reason is because A reduces the energy. It takes you down one level. And A dagger, this cross right here, is a dagger. A dagger lifts you up one energy level. They're also called creation and annihilation operators in particle physics and quantum optics because they create or destroy a particle or a photon. But that's a story for another day. So if you take the product of these two operators, A and A dagger, this is what you get. And if you rearrange the terms, this is what you get. Now, this might look kind of funny. I've got xp minus px, and you might think, well, that's just 0. Well, it's not, because the order matters when you're taking derivatives and multiplying by functions. The order matters. So xp minus px, this should be familiar from my introductory remarks. This is the commutator of x and p. It's xp minus px, and it's written this way with the square brackets. So this is the product of A and A dagger. Now, xp minus px is not, xp does not equal px, and so the difference is not equal to 0. And the way we describe that is we say that position and momentum don't commute. The value of the difference is non-zero. So these are operators. So how do we analyze an operator? Well, you apply it to a function, because that's what operators do. So I've got the commutator here. I apply it to this function f. F is just any function. The equations I'm about to derive are true no matter what function f is, as long as it's reasonably well behaved. If it has a jump in it, then that would be a different story. But wave functions are continuous. They don't have jumps and breaks in them. So substituting the definition for the commutator, I get this. Here's x. Here's p, the momentum operator. We apply it to f. Here's the momentum operator on the left and x on the right. What this means is we multiply by x first, and then we apply the momentum operator. X is the position, the distance from the center. It's also called the position operator. Now there's a rule from calculus that says that if you take the derivative of the product, you get two terms. And these are the two terms you get if you take the derivative of x times f of x times a function. You get the function plus x times the derivative of the function. So the derivative terms cancel. And what you end up with is just IH bar times the function itself. Now, as I say, this equation 14, is true for all functions f. And the function f appears on the right here, and it appears on the right here. And so what that means is we can remove f of x from the left side and the right side. And if you remove it, this is what you get. So we've computed the commutator of position and momentum of x and p. It's a number. It's IH bar. If you apply it to a function, it just multiplies that function by the square root of -1 and h bar Planck's constant. So this equation is famous. It's called a canonical commutation relation. One meaning of the word canonical is conforming to a general rule or accepted procedure. So this rule and other canonical commutation relations are so important and so powerful that Heisenberg in the 1930s was able to derive all of quantum mechanics using these commutation relations. This is the famous matrix mechanics, which is a topic for another video. Now, inserting that commutator into equation 11 right here, this is what you get. This is the Hamiltonian. It's the the thing that governs the behavior of the system. And this is a very beautiful equation. It's very simple and it's very powerful. Now, speaking of commutators, what's the commutator of A and A dagger? Well, we just substitute A and we substitute A dagger, put them in both orders and take the difference. What you get is 1 plus 1, and you get half of that. So the commutator of A and A dagger is 1. And by the way, if you get into big complicated derivations, it's helpful to keep the A's on the left and the A daggers on the right. This is called normal ordering. Plugging this into the expression for the Hamiltonian, we get this. This is the equation that is going to save us from having to solve the differential equation. And here's the magic part. If the wave function satisfies Schrodinger's equation, then A dagger times the wave function satisfies the same equation, but with a different energy, with a higher energy. The energy is increased by h bar omega. And I've proven it right here in equations 20 and 21. So here, I just substituted the expression for the Hamiltonian. There should be an A dagger right here, which is omitted due to a typo. But I've got it here, so this is what you get. And you see you have A dagger on the left in both terms. It's a linear operator, and what that means is that if it's on the left for two terms, you can move it outside the sum. So that's what I did. I moved it out here before the parentheses, and I get A dagger plus 1/2 psi. And if I apply the commutation relation, the commutator of A and A dagger is 1, then this is what I get. Now I've just rewritten equation 20, the left side, this term, and this term, and this is what I get. I used equation 18, the commutator, and the fact that E plus h bar is just a number. It's an operator that just multiplies, and it's constant, so derivatives don't affect it. And what that means is that I can change the order. It commutes with everything. And so this is what I get. And if you look at this, this says that the Hamiltonian, acting on A dagger psi, gives you back a multiple of A dagger psi. So this is another eigenvalue equation. And the eigenfunction is A dagger psi, and the eigenvalue is E plus h bar omega. This is just Schrodinger's equation all over again, but with E replaced by E plus h bar omega. So what we've done is we've taken a wave function with an energy level E, and we've converted it to a wave function with an energy level E plus h bar omega. And that's why A dagger is called a raising operator. It raises the energy. You can do similar algebra to show that A lowers the energy. It reduces it to E minus h bar omega, so it's called a lowering operator. However, have a look at this potential energy curve. It has a minimum. It never gets below 0. And what this means is that you can't keep lowering the energy and making it more and more negative. There has to be a stopping point. There has to be a minimum energy. And so what that says is there's got to be some wave function that if we apply the lowering operator on it, it just kills the state. It gives us back 0. not even a quantum state. If we were dealing with photons, it would be like, okay, there was one photon left, and we applied the annihilation operator, and now there's no more photons. There's just a vacuum. There's nothing there. So this is what it means. A, or A hat, I should be saying hat all this time, but I got lazy. I just call it A. A hat times the wave function psi gives you 0. A hat applied to the wave function psi gives you 0. Now, if you substitute the definition for A hat, this is what you get. Now, this momentum operator P takes a derivative. So you put in that definition, and you get equation 23 right here. This is a first-order differential equation. And it's very simple to solve. You can integrate it directly, and this is what you get. The wave function, and I've called it psi 0 to indicate the 0 indicates it's the lowest energy level. It's some unknown constant A times this exponential. And what this looks like, it's a famous bell-shaped curve, familiar from statistics. It's also called a Gaussian, after Carl Friedrich Gauss. Carl Friedrich Gauss, the brilliant mathematician. Well, we have to determine A. It's an unknown constant. And the rule is that if you take the absolute value, the modulus of the wave function squared, that gives you the probability per unit distance of finding the particle in that location. Well, if you sum that up over all locations from minus infinity to plus infinity, all possible locations, you have to get certainty because you have to get 1, which is certainty, because the particle is certain to be somewhere. We just don't know where, but we know that it has a location in space. So equation 25 is the normalization condition, and it has to be hold true, and it determines the value for A. And if you do the integral and plug it in, this is what you get for A. M omega over pi h bar raised to the 1/4 power. 1/4 power is the square root of the square root. So now that we know A, this is what the wave function is. I've written it psi. Technically it should be psi 0 because it's the lowest energy, which is also called the ground state. Here's the wave function again. Now, wave functions in general are complex numbers, so you can't plot them. But for the harmonic oscillator, the imaginary part is always 0. So we just plot the real part. Now, if you plug this back into Schrodinger's equation, you can determine the energy level. The ground state energy, E0, and it's 1/2 h bar omega. Well, that's interesting. The minimum energy is greater than 0. What does that mean? Well, it means that the particle is jittering. It can't stop moving. This is a consequence of the Heisenberg uncertainty principle. The momentum and the position have to have some finite possibility of departing from 0. Now, what about the other states? You can go up the ladder by repeatedly applying the raising operator so that the nth state, also called the excited state, is given by equation 29, and the nth energy is n plus 1/2 times h bar omega. From here on, you can go on up the ladder by repeatedly applying the raising operator so that the nth state, also called an excited state, is given by equation 29. You have an, that's a constant. It's determined by normalization the same way we determined a. You have the raising operator to the nth power. That means it acts n times. And you start off at the lowest energy, the ground state. So the nth energy is n plus 1/2 times h bar omega. And figure 6 shows the energy levels and the wave functions. Right here. Here's our Gaussian bell-shaped curve. Notice that some of these, if you reflect it about the center, the sign changes. So that's antisymmetric or odd. Some of these, like the ground state, if you reflect it about the center, you get back the same thing you started with, so that's even. This is referred to as parity, and it's a very important conservation law in physics. So if you work out the factors, then you get the nth wave function is equal to a dagger, this should be to the nth power, applied to psi 0, the ground state, with a factor of 1 over the square root of n factorial. What n factorial is the factorial function. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. So this completes the explanation of the Dirac method of solving the harmonic oscillator. I refer you to the companion video that's linked in the description for more information about the wave functions. You can also go to Griffith and you'll get a little more information. So if you like this video, if you found it interesting or helpful, please subscribe. And to be notified of upcoming videos, enable notifications. Click on the bell. Thank you for joining me today, and have a good week. Have a good holiday. Thank you.